Good afternoon. Okay, again, resuming with equations, and again, just going back to the early days, we were looking at the FOIL method and then factoring, and we looked at modes of various types in terms of combining terms, some direct terms, some fractions, and then we made the crossover to working with equations where we had categories like conditionals, contradictions, as well as identities, and then we cross over to the quadratic equation and looking at the various types of solving those, and also we made a transition to working with radicals, and we are going to get back to that shortly. And most recently, among the last topics we have delved into, we had to include absolute value equations, and referencing what we have in section R5, okay, and we have from page 70, okay, and again, absolute value, okay, is going to be a non-negative quantity, and where we have absolute value equations, okay, we have the key fundamental, okay, whereupon if you have a constant k to be a non-negative value, that is where it is 0 or higher, and we have that the absolute value of x is equal to k, then you're going to have x to be equal to plus or minus k. And now for what we have in the set from page 70 concerning absolute value equations, we have in number 90, okay, we are looking at solving for the variable t. In the statement we have 4 times the absolute value of 2t plus 7 followed by the addition of 2 is equal to 22. Again, we're looking at solving for t, and just a reminder with absolute value notation, okay, you do not treat the bars as you would parentheses. Okay, so in other words, what I'm saying here is that we're not to distribute in other words, do not distribute, say, like 4 over the absolute value of 2t plus 7. It'd be kind of nice if you could, but since we're dealing with absolute value, okay, we're looking at a different situation, okay. And so what we're going to do is that we're going to get the representation of the absolute value of x by itself. So this is going to be the absolute value of 2t plus 7. All right, so moving ahead, okay, so we have a couple of obstacles here. We have the multiplication by 4 and the addition of 2. And if we start out, okay, in the process of isolating the absolute value of 2t plus 7, okay, I can take 2 away from both sides. So I have 4 times the absolute value of 2t plus 7 is equal to 20. And to take care of the 4, I'm going to divide both sides by that amount. And in the case of simplifying, see, we have upon canceling out the 4's, we had the absolute value of 2t plus 7 is equal to 5. Okay. So you have this particular framework, absolute value of x, we have the absolute value of 2t plus 7, and we have is equal to k, where k is 5 and k is non-negative in value. So we can proceed. And with 2t plus 7, okay, I can remove the absolute value grouping symbols. So we have 2t plus 7 set equal to those values that will have an absolute value of 5. Okay, so the two numbers with the distance of 5 units away from 0, we're going to have both 5 and negative 5. So we're going to have a couple of distinct outcomes for t. And we have at the lower end, we're going to have that 2t plus 7 is equal to negative 5. And we have at the upper end, okay, we have that 2t plus 7 is equal to 5. And we have, in the case of the simultaneous equations, okay, so if I get 2t by itself, and we have deducting 7 from both ends of both equations. Okay, we have, for the first equation, we have 2t is equal to negative 5 minus 7. So this will end up at negative 12. And we have a division by 2. Okay, we're going to have that t is equal to negative 6. And for the second equation, okay, we have 2t is equal to 5 minus 7. Okay, so this will be at negative 2. And we have with division by 2, okay, we have that t is equal to minus 1. And just looking at what we have here, and you can do like a little bit of double checking. Okay, so we have with t at negative 6, okay, we have 2 times negative 6 is negative 12. In turn, negative 12 plus 7 comes out to negative 5. Now, just think about this. Okay, so we had the absolute value of negative 5, which is going to be positive 5. And we have 4 times 5 is 20, and 20 plus 2 is equal to 22. So we have consistency where t is equal to negative 6, and for t is equal to negative 1, we can have 2 times negative 1 is negative 2, plus 7 is 5. And just like negative 5, okay, the absolute value of 5 is going to be at 5. 4 times 5 is 20 plus 2, and we also have at 22. Okay, so t has 2 solutions, okay, with negative 6 as well as negative 1. Now for what we have in the case of number 91, okay, we're going from solving for t to solving for the variable c. And in the case of 91, okay, we have in this setup, we have that negative 3 is equal to the negative of the absolute value of c minus 7 followed by the addition of 1. And again, you just leave the absolute value of c minus 7. Do not distribute any negative sign over c or negative 7. And if we isolate, okay, so we can undo the addition of 1 upon taking this amount away from both sides. Okay, so for what we have at this stage, okay, now we got negative 3 minus 1, which will be negative 4. And we have is equal to the negative the absolute value of c minus 7, and we're going to change the signs at both ends. So you can either multiply or divide the equation by negative 1. Okay, so we have a sign change at both ends. And so we're going to have that 4 is equal to the absolute value of c minus 7. Okay. And I'm just going to switch the order of the terms in this equation. Kind of like logically the same, just going from b is equal to a is equal to b. And just have the variable expression on the left. Okay, so I had the absolute value of c minus 7 is equal to 4. So we had the absolute value of x represented by the absolute value of c minus 7. K is 4, which is non-negative. And so freeing up c minus 7 by removing the absolute value bars, we have c minus 7 equal to the amounts that are 4 units away from 0. So we have equal to plus or minus 4. And setting up the equations. So we have at the lower end, okay, c minus 7 could be negative 4, and at the upper end we had that c minus 7 could be equal to 4. And looking at isolating c, okay, so we have adding 7 throughout. Okay, so we have for c minus 7 equal to negative 4, then we have c equal to negative 4 plus 7. Okay, so that is equal to 3. And for c minus 7 equal to 4, adding 7, so we had that c is equal to 11. And again, there's really no pressure to double check your answer as you would if you had like an even root radical equation, but you can still check. Okay, so if I have c at 3, 3 minus 7, okay, is negative 4. Now the absolute value of negative 4 is a positive 4, but in spite of the absolute value being positive 4, okay, we're going to have negative 1 times that. So you have a negative 4 plus 1 on the right, and we have equal to negative 3. Now for 11, we have 11 minus 7 is 4. The absolute value of 4 is 4. But again, you have multiplying by negative 1 thanks to the minus sign in front of the absolute value symbolism. So you got minus 4 plus 1 again, which is going to be negative 3. So those are the two results we have in C. Now, for what we have in the case of number 93, okay, this time we're looking at trying to solve for y. And we have in this equation, so you have 2 is equal to 8 plus the absolute value of 11y plus 4 and I want to get the absolute value term by itself. Okay, and so I can do this, okay, removing 8 and deducting this amount, okay, from both sides. Okay, so I have 2 minus 8 is negative 6, and to the right I have the absolute value of 11y plus 4. And again, I can just switch the order, and again, this is optional. Okay, we're just having this as a bit of an analogous reference to the absolute value of x is equal to k. So you have the absolute value of x represented by the absolute value of 11y plus 4, and k, okay, we have it negative 6. And if you notice, okay, k is supposed to be a non-negative value. Now look at what we have for k. We have a minus amount. Okay, so and since k is at negative 6, okay, we have a problematic situation. Anytime you have k to be negative after the absolute value term is isolated, automatically you have no solution. All right, now for number 94. Okay, so we have looking at an expression in y going out to an expression we have in the letter z. Okay, so we got for number 94, okay, we have that 6 is equal to 7 plus the absolute value of 9z minus 3 and if I get the absolute value term by itself, okay, so just as I subtracted the leading coefficient from the right hand side, I'm going to do likewise here. So taking 7 away, so I have 6 minus 7 is at negative 1. To the right, after canceling 7's out, I have the absolute value of 9z minus 3 And again, switching the order, so the absolute value of 9z minus 3 is equal to negative 1. And we're back to where we have the absolute value of x is represented by the absolute value of a binomial. And again, we have our k value to be negative. And so we have history from number 93 to repeat, where we're trying to set an absolute value term equal to a negative constant. And that cannot be done, so we have, once again, no solution in the problem. All right, now, different kind of setup, okay, for number 96. Okay, and in this one, you have what would be two absolute value terms said to be equal to each other. So we got the absolute value of 2a minus 3 is equal to the absolute value of a plus 2. And let me mention something here. Okay, so you got the left-hand side. So the absolute value is going to be like 2a minus 3 units away from 0. And this could be like the positive and negative. Let me just kind of pause here. Say if I have like the just like if I had earlier, okay, so I had like absolute value of x is equal to 7. Okay, you have like x could be plus or minus 7. And just on a parallel course, okay, if I have like the absolute value of x equal to 2a minus 3, x could be equal to plus or minus the quantity of 2a minus 3. Okay, and what I'm going to do here, okay, so it'll be 2 units. Okay, that would be 2a minus 3 units. So I have plus or minus 2a minus 3, and for a plus 2, okay, we have plus or minus the quantity of a plus 2 and to solve for a, what I can do, okay, now you have up to 4 possible statements, but I need only 2, okay, where you have like opposite sign terms or opposite sign expressions, and also same sign expressions. And what I mean by here is that, say if I work with the positive of 2a minus 3 and set this equal to the positive of a plus 2, I can have this mapping. And also, if I take the positive 2a minus 3, I can map this with the negative of the quantity of a plus 2. Now, again, there are up to 4 distinct possibilities, but I just need 2 of these combinations. I can have like a negative of this to the positive of that, and negative for both of these. But it's just going to be repetition of the previous 2 cases. So just taking what we have here. Okay, so I got like the positive of 2a minus 3 is equal to the positive of a plus 2, and the other possible equation in the variable a, and say that I have the positive of 2a minus 3 equal to the negative of the quantity of a plus 2. Okay, so no sign change whenever we have both sides to be positive. So you have 2a minus 3 is equal to a plus 2. All right, so you have two sets of like terms on opposite sides. Okay. And to set this up and solve for a, so got 2a and a, and I can just take away the smaller variable term. So I got 2a minus a is going to be a. And we have that a minus 3 is equal to 2. And just adding 3 to both sides, so we have a solution with a equal to 5. Now for the other combination, okay, so you have left-hand side, okay, there's no sign change. So you have 2a minus 3. Now for the negative of the quantity of a plus 2, so you're going to have negative a minus 2 and if I combine like variable terms, okay, so I'm going to this time add a to both ends. Okay, so you have 2a plus a becomes 3a so you have 3a minus 3 is equal to negative 2. And if I isolate 3a, okay, so adding 3 to both sides, so I have 3a is equal to 1, and we have with division by 3, okay, so we have that a is equal to 1/3. Yes. Question?
So what you're saying is basically like when you rewrite the equation, you can just do 2a minus 2, the absolute value of 2a minus 3 equals plus or minus a plus 2. Like you don't necessarily have to do the plus or minus on both sides. You can just
in other words, like had the same sign. In other words, have like plus plus and plus minus. In other words, same sign. You could be just one with same sign and the other combination with opposite signs, and you're good to go.
Yeah, because what I did was I basically just treated it like the other ones that we did, and I just did the a plus 2 as one unit and just did that as plus or minus. And I got the same answer. I just want to make sure that I can continue to do it that way.
Right. Yeah. Okay. If you have, in other words, like you said, if you just had 2a minus 3 equal to a plus 2, and 2a minus 3 is equal to negative a minus 2, if you did it that way, it's the same. It's the same premise.
All right. Thanks.
And basically, if you ran it through the other, like had negatives on both sides, and then had the negative of 2a minus 3 equal to, the negative of a plus 2, you're going to have repetition of the same answers. And it's kind of like, probably not the best parallel, but it's kind of like changing a dollar bill, like 3/4, 2 dimes, and a nickel. And you give the quarters first, the dimes next, and the nickel last. But if you gave it like nickel first, 2 dimes in the middle, 3/4 at the end, or 2 dimes at the front, 1 nickel, it's going to be the same currency items, and so just these two sequences here, that takes care of all the answers. Okay, so we do have a at 5 and also at 1/3. Okay. All right. Now, for what we have in crossing over, okay, just going from what we have in absolute value equations, and at the start I did mention that we'll be looking at going back to radicals. And this next part, quite a few topics in sections R5 and R6. You can have a lot of interchanging like between radicals and absolute value. And now you're having crossover going back to radicals in the capacity of where you have equations with non-integer exponents. And this could be done in various, non-integer exponents. There's non-integer could go out in several different directions. But what I mean by non-integer in this case would be like fractions that cannot be reduced to integers or whole numbers. And just a little bit of a backdrop. Say if you have an exponential base a. And so you have raised to the m over n degree. And I express this in radical terms. Now, we have with m over n, now the index number, or the type of root, is going to be indicated by the bottom part of the fraction in the exponent. So you have the denominator is going to be n. So as a radical, we're going to have the nth root of the exponential base a to the m power. So a to the m over n is equal to the nth root of a to the m. And just giving you visuals in terms of reduction from fractional exponents, to the radical equivalent. If you have something like, let's say we have x to the 3 halves. So m is at 3, n is at 2, a is represented by x. So the nth root is going to be the second root, and that's just going to be a square root. And that's going to be the square root of x to the third so this comes out to x, the square root of x to the third. And let's say if you have y to the 4/3. Alright, so the denominator in the fraction is going to be at 3. And translating y to the 4/3 to its radical equivalent. So we have the cubic root of y to the 4th. And that's going to be your result here. Now I could technically reduce the radical, but just looking at the immediately translating components, like going from non-integer exponent to the radical equivalent, this is going to suffice at this stage. And now I can have also an expression, such as z to the 5/8. And this is, now the first two cases you had the top part of the fraction to be greater than the bottom, but now we have n to be greater than m. So you have z to the 5/8, and 8, this is the kind of root we're going to have here. So we're going to have the 8th root of z taken to the 5th. So this is what we have here in translate, and the purpose this is going to serve is once we get or cross over to equations that have non-integer exponents. And let's say that if you're looking at solving for x, and we will say here that x would be such that, let's say we have x to the 1/2 is equal to 8. So you have for x to the 1/2. And if I were to rewrite in radical terms, I'm just going to take this little extra step. So you have the second root of x to the 1st But again, that's just going to be the square root of x is equal to 8. Okay, so we're going to go from the square root of x to x. So to get rid of the square root, I'm going to square both sides. And for the square root of x squared, this becomes x, and 8 squared becomes 64. And let me pause. Okay, now we had an even root radical set equal to a constant. And again, an even root radical expression cannot reduce to a negative constant. Okay, so starting out with fractional exponents, if the radical is of an even root, again, you cannot have it to reduce to a negative constant. So again, we were able to work this one through, and the value of x is 64. And let me mention, if you were to test out 64 to the 1/2, so if you were to take 64 and you were to put this in terms of a fractional exponent, okay, and for many models, including the TI variety, if you were to enter the exponent in the form of a fraction, do not forget to put the fraction in parentheses. If you don't, it would just read it as 64 to the first power, which would be 64 divided by 2, which would come out to 32. So if you did that and said, why is 8 not showing up, you would just need to put the exponent in parentheses. All right, so 64 to the 1/2, okay, is equal to 8. Now, and let's say that for just a case here, changing up a little bit, if I have 3 times the quantity of 2x plus 2 raised to the 1/3 is equal to 12. And if I get the variable expression base, okay, by itself, so I'll just move the 3 by division. All right. So we got here. So we had the quantity 2x plus 2 to the 1/3, okay, is equal to 12/3, okay, which will go to 4. Okay, so m is at 1, n is at 3, and the denominator signals a kind of radical that this term is going to have. So you're going to have the cubic root of 2x plus 2. 2x plus 2 to the first, which would be 2x plus 2. And we have this equal to 4. And again, if I had negative 4, I could still continue on the basis that the principal square root rule does not apply to odd roots. Now, in taking care of the radical, I'm going to take both sides and raise to the power that matches the index number. So I'm going to be looking at cubing both sides. Okay, so cubing out the cubic root of 2x plus 2. So we have 2x plus 2 and 4 to the 3rd power. So I'm going from 4 to the first at 4. 4 squared is 16, and times 4 will be 4 cubed, which will be 64. And now we have taking 2 away from both sides. So we have that 2x is equal to 62, and we have with division by 2. Okay, we're going to have that x is equal to 31. Now, let's say that in looking at another scenario, okay, if I have, this is just kind of used to, or will be used to just reinforce okay, a key fundamental. If I had the x minus 5 to the 1/2 is equal to -7. Again, just translating in radical terms. So this is going to be the square root of x minus 5. We have is equal to -7. So I have an even root radical, and notice I'm trying to reduce an even root radical where it is equal to a negative constant. Okay, and so this is going to be forbidden. Okay, and because of the negative sign, okay, there's going to be no solution. And I'll just take this, okay, so just modifying this the least bit. If I have the quantity of x minus 5 to the 1/2 is equal to 7. Okay, so you have x minus 5 to the 1/2 is going to be the square root of x minus 5 is equal to 7. So here I have a positive 7, and I can reduce an even root radical to a positive. So if I square both sides, okay, so we have x minus 5 is equal to 49, and with adding 5, it's going to turn out that x is equal to 54. Again, 54 minus 5 is 49. 49 to the 1/2 would be the square root of 49, which would go to 7. All right. Now, let me give you one where, okay, so far we've either had no solution or positive results, and whether or not we can have more than one solution for x. Okay, let's say we have x minus 6 to the 2/3 is equal to 4. Okay, so if I take what I have here and translate in terms of a radical, okay, so the type of root, okay, we have with the denominator. Okay, so you have the cubic root of x minus 6 to the 2nd is equal to 4. So I got a cubic root, and I can take care of the cubic root like what I did here upon cubing both sides. Yeah, the terms are getting a little bit crowded, especially with the exponents included. Okay, so I'm cubing both sides, and you have like a bit of history to repeat from the second example. Again, cubing 4 is 64, and we have freed up, we're going to have the square of x minus 6. So I got the square of x minus 6 is equal to 64, and so there are various ways you can follow through. You could square x minus 6, deduct 64, and have a quadratic equation that is in standard form. Or you could take the square root property of equality. Okay. We have like x squared equal to a constant. You have x equal to plus or minus the square root of that constant. So you got like x squared represented by the square of x minus 6. And if I drop this down to just the first order of x minus 6, okay, so this will be equal to plus or minus, okay, the square root of 64. And I have that x is equal to plus or minus 8. And just setting up simultaneous equations where I have x minus 6 equal to -8, and also x minus 6 equal to +8. And if I look at adding 6 to both sides, So we want to have two distinct outcomes. Okay, so here we have negative 8 plus 6 is negative 2. For x minus 6 equal to 8, okay, we have x equal to 14. And those will be our two results here. So you have with negative 2 and positive 14. And I'll tell you what, just for working with radical equations or that originate from non-integer exponents. So let's see what we get. First of all, okay, say we have 2 times the quantity. Okay, say we have x plus 5 to the 2/3 is equal to 18. And also just a little bit of a kind of a partial multi-step. Let's say we have 2x minus 2 to the 3/2 minus 3 is equal to 5. So for the next few moments, let's see what we get for x in these equations. The setup, if you're still working on these, that's fine. But for what we have in the case of the first item, okay, so we're looking at 2 times the quantity of x plus 5 raised to the 2/3, okay, is equal to 18. Okay, and tell you what, if I isolate the variable expression just to take care of the coefficient 2, you could probably say that in a way it's sort of like pre-isolating the radical. So we have the 2's to go out on the left. Okay, and so we have the quantity of x plus 5 to the 2/3, okay, is equal to 18/2, okay, which is going to be at 9. All right, so again, we're back to just like the last example. Okay, we had an expression to the 2/3 power equal to a constant. Now we have x plus 5 raised to the 2/3, and if I rewrite as a radical, okay, so we have the 3 signals that we're going to have the cubic root. And what's that going to be the cubic root of? Well, that's going to be x plus 5 raised to the m power, where m is going to be at 2. So I have x plus 5 raised to the second. And we have this equal to 9. Okay. And okay, so this is the radical notation translation. And I can take care of the cubic root upon cubing both sides. So the exponent and the index number radical will cancel each other. All right, so on the left, okay, so what's going to be left standing will be what was underneath the radical. And so that is going to be x plus 5 raised to the second. Now for 9 to the third, okay, we're going to have a fairly large number. Okay, we have 9 to the first is 9. 9 squared is 9 times 9, which will be 81. And for 9 to the third, you're going to have 9 times 9, 81 times 9, which will be 729. And now we have, with crossing over to the stage, okay, with the square root property of equality. So if I go from the square of x plus 5 to just x plus 5, And so we have plus or minus, okay, the square root of 729. All right, and 729, okay, that, like other numbers, like 664, okay, will be both a perfect cube as well as a perfect square. Like 729 will be 9 to the third. And guess what? 729 is going to be the square of 27. Since 27 times itself comes out to this 3-digit product. And so we have for x plus 5. Okay, this is going to be equal to plus or minus 27. And now setting up the equations and solving for x. So we're going to have at the lower end, okay, we have the x plus 5 is equal to negative 27. And for what we have at the upper end, we have the x plus 5 is equal to positive 27. And if I take 5 away from both sides in both equations, okay, so we have x is going to be negative 27 minus 5. So this is going to be negative 32. And for x plus 5 equal to 27, again, take away 5. And we're going to have the result here, whereupon we're going to have that x is equal to 22. And so we're going to have, in these results, okay, we'll have two solutions. Once again, for x with negative 32 and positive 22. Okay. Now, in the second case, all right, so we got the quantity of 2x minus 2 to the 3 halves minus 3 is equal to 5. And if we look at, okay, just like isolating the exponential term or expression, so I'm just going to add 3 to both ends. Okay, so this is going to come down to 2x minus 2 to the 3 halves. We have is equal to 5 plus 3, which is going to be at 8. All right. Notice, okay, we have 3 halves and 2/3 are reciprocals of each other. Now I have the exponential expression by itself set equal to a constant. And if I translate this term to its radical equivalent, okay, now the type of radical is indicated by the denominator, 2. So we're going to have a square root. This time this will be the square root of 2x minus 2 raised to the 3rd power. All right, so this time we have the radical to be a square root, and we're going to get rid of the square root like what we did from the other day. Okay, and that's going to be to square both sides of the equation. Okay, so that's just to get rid of the square root. All right, so squaring both sides. Okay, what was inside the radical? Okay, so we have 2x minus 2 quantity to the 3rd power. And to the right, we have 8 squared, which is going to be 64. Okay, now, and we have here for the cube of the quantity of 2x minus 2, we have equal to 64. Now there's going to be a sudden shifting of gears, kind of going in opposite directions. Now, we got rid of a radical by taking an exponent. And guess what? We got an exponent, and I'm trying to free the x expression away from the parentheses where I have the whole entity raised to the 3rd power. So guess what? I took an exponent to get rid of a radical earlier, Now I'm going to do it the other way around. So how do I get rid of the cube? That's going to be to take a cubic root. Okay. So in this case, right, so I want to have 2x minus 2, not 2x minus 2 to the third. So for what I have on the left, okay, so we have radical cancels out the exponent. So we have 2x minus 2. Now as for the cubic root of 64, okay, like 729, 64 is both a perfect square and a perfect cube. Think of it like this, okay, so you have the cubic root of 64. Now 64 would be 4 times 4 times 4. And guess what? This would be like the cubic root of 4 to the third power. And again, the radical and the exponent would neutralize each other. So that just becomes 4. So cubic root of 64 is going to be at 4. And so we're down to a single equation. Okay, where 2x minus 2 is equal to 4. And we have, upon adding 2 to both sides, okay, so we have it 2x is equal to 6, and we have a division by 2. Okay, so we have the value here to be a 3. Okay, and so that is going to be our solution. And let me just mention, okay, when we had a square root, okay, the constant of which it was set equal was a positive, so I was able to proceed. Okay, all right, so we had the x is equal to 3. Now, looking at, okay, just a little bit of a revisit of an absolute value equation that has absolute value terms on opposite sides here. Okay, so you had the absolute value of 2x minus 4 is equal to the absolute value of x plus 8. Okay, and let's say that if your approach is to say, I'm going to set up two equations, but let's say if I want to keep it just 2x minus 4 in both cases, which can be done. Okay, so we have for 2x minus 4, again, your possible combinations. Okay, plus or minus the quantity of 2x minus 4 and for x plus 8, so if I take the plus or minus of x plus 8, okay, so I took out the absolute value bars. Okay, so yeah, plus or minus the quantity of 2x minus 4 equal to plus or minus the quantity of x plus 8. And say if I want to work with 2x minus 4 in both cases, so just have directly, say if I have 2x minus 4 equal to x plus 8, where all the terms will be positive throughout. And again, if I keep 2x minus 4 as it is, no sign change up, and just have it mapped with the negative of x plus 8. Okay. So you only need two combinations. Okay, one combination where we have same signs and just a separate combination with opposite signs. So I'm just keeping positive unanimously for the left-hand side and alternating, okay, between positive and negative on the right-hand side. Okay, so removing the parentheses. So we have 2x minus 4 is equal to x plus 8. And solving for x. Okay, so if I gather together the x terms, and I can take out the smaller one, which would be x, and 2x minus x becomes x, and I have x minus 4 is equal to 8, and if x minus 4 is equal to 8, okay, we're going to have the x is equal to 12. And you can do a quick check. 2 times 12 is 24. 24 minus 4 is going to be 20. Absolute value of 20 is 20. To the right, and got 12 plus 8 is 20, and its absolute value is 20, so both sides are at 20. Now, for what I have with a plus and minus combination, okay, so I'm still keeping 2x minus 4. No sign change in this one. Now to the right, I'm going to be taking the opposite sign, or the negative of x plus 8. So this is going to be negative x minus 8. And if I combine variable terms, okay, so this time I'm going to add x to both ends. So we've got 3x minus 4 is equal to negative 8, and it looks like we're going to have a fraction in the mix on this one. Okay, so you have 3x minus 4, and if I add 4 to both ends, so we have 3x is equal to negative 8 plus 4, which would be negative 4. And we have with division by 3. Okay, so we have that x is equal to negative 4/3. Okay. Now just mention just a quick glance. Think of, okay, so you have x at negative 4/3, and think of 8 as being 24/3. Negative 4/3 plus 24/3 is going to be a positive 20/3. Absolute value is at 20/3. Now for negative 4/3 here, 2 times negative 4/3 is a negative 8/3. And think of 4 as being 12/3. So you got like negative 8/3 minus 12/3 is a negative 20/3. And the absolute value of negative 20/3 is going to be 20/3. So you have 20/3 equal to 20/3. Okay, and so those will be the two solutions we have for x in this particular absolute value equation. All right. Now, just remaining item, and we have dealt with thus far, okay, the real number system, and sort of just combining with what we have had with radical elements. And we have what would be referred to, okay, this can be outside the set of real numbers. And we'll be having here, okay, what will be referred to as the complex number system. And the centerpieces for this, okay, now some books might use the letter J, but most books I have seen use the letter I in the complex number system. What does I refer to? Well, this is going to be a number that's not in the system of real numbers, and that's going to be the square root of -1. So you have I is equal to the square root of -1. And if I were to square both sides, okay, so I would have the I squared is equal to -1. Okay, so how am I going to work with I? Well, as introductory cases, okay, so if I were to reduce the following, in terms of I, and we'll start out with something fairly user-friendly. If I have, let's say, the square root of -25, so you got something that is a perfect square with 25. And say if I were to separate, you have like 25 times -1. We have the square root of 25 times the square root of -1. Now, the square root of 25 is going to be at 5. And anytime you see like the square root of -1, that's going to become I. So you have, while the square root of 25 is 5, the square root of -25, okay, that is going to become 5i. And say if you have something like the square root of -100, so just working with another perfect square, so you have like the square root of 100 times the square root of -1. Again, square root of 100 is 10, square root of -1 is going to be I. So you have altogether the square root of -100 is equal to 10i. And let's say if we have something that is not quite a perfect square number inside the radical. Say if I have the square root of -28, okay, so I had the square root of 28 times the square root of -1. Now again, 28 is not a perfect square, okay, but it is the multiple of a number that's a perfect square higher than 1. Say like for the square root of 28, think of this like the square root of 4 times 7. So you have the square root of 4, which is a perfect square. 7 is not a perfect square, so that part stays underneath the radical. And the square root of -1, we can write this as I. And for the reduction, we had the square root of 4 is at 2. And we have times the square root of 7, and we have times I. And I think this would be Alex's more common notation, but I think it will also take, some of you might have seen complex numbers before and have the variable in front of the radical. So another possible notation would be 2i times the square root of 7, but I think I see this formation more frequently. All right. And again, we have with complex numbers, you can have I is equal to the square root of -1. Again, if you square both sides, you have I squared is equal to -1. Okay, now for what is referred to as the standard form of a complex number, the standard form of a complex number is going to be a plus bi. And we have with, let's say with this final example, let's say if you write in terms of a plus bi. And we'll say we have like 3 plus the square root of negative 49. And we'll say we have plus the quantity of 7 minus the square root. And we'll say we have negative 144. Okay, so I have square roots of negatives. And if I go ahead and write in terms of the letter I, okay, now square root of 49 is 7, but with the negative 49 underneath. Okay, square root of negative 49 is going to be 7i. And we have plus the quantity, so we got 7 minus. Now the square root of 144 is 12, but for negative 144, it is going to be 12i. And say if I remove the parentheses, okay, so I have 3 plus 7i, and we have plus 7 minus 12i. So there was no negative or subtraction to distribute, so no sign changes here. And you can mentally combine your constants and I terms. And I'm just going to move the constants to the front, just add in this extra step here. So you got 3 plus 7, and for the complex terms, they have 7i and negative 12i. And for the a plus bi form, okay, so we have 3 plus 7 is 10, and 7i minus 12i, we have minus 5i. Okay, so like your a would be at 10, and bi would be where b is negative, where we have minus 5i. So this is a sample of what we have with a complex number that is in standard form. So you have just a coefficient, numerical coefficient, and then following this will be an I term, like in the case of 10 and negative 5i.